So here, so this is equal to the combination of QV cross B.
Is that velocity?
So this is the velocity, right? So this is the velocity, that's the magnetic field, that's the charge. So we saw, we looked at the electric, if you charge something by rubbing it with some felt or some sort, you have an electric charge on here. If you bring a magnet close to this, there will be no force. If you have something that's moving without a charge like a bird, no force. If you have a charge that's moving, there's a force. How odd is that? So you need a moving charge, then there's a force caused by a magnetic field. You need this combination in QV cross B. And in terrestrial conditions, in most common everyday life experiences, this is by far the strongest force. Gravitational force becomes high when you're huge masses. So when you're talking about planets and moons and stuff like that, this is always the winner. On a cosmological scale, the gravitational force basically overcomes everything else. The electric force in terrestrial conditions you saw was very feeble. You can charge things together with friction and all that. The best you can do is pick up lint or tiny pieces of paper. It's a very feeble force. But the magnetic force, it moves cars. I arrived at work today driving an electric car. That force was the magnetic force. Huge difference in the magnitude of these forces under normal everyday conditions. So for comparison, for gravity, you need a relatively big object for there to be a noticeable force. But the magnetic force, look how small and light these things are. So I'm going to let you compare the gravitational force with the magnetic force. So pull these things apart and you'll get a sense of how strong the magnetic force is. First I'm going to pass this, so you'll experience these things from 201. Whoever the next person is, have a hand under this so that you don't drop it and cause a mess. Take one hand below and hold this with the other hand. This is what I meant. Okay. It seals, it's not going to leak. So, grab it with one hand, keep one hand below. I'll do that. Okay. Which one are you going to grab it with? You see? That's it.
Yes. I thought soda can. Why is it so heavy?
I knew your Pepsi can, right? Now, look how small this is, right? I mean, it weighs practically nothing. Like a couple of cubic inches inside. Feel the force between these two magnets. Put them apart. If you're not prepared for it, if you grab it with one hand, you know the weight.
Superman's favorite. It's like some metal.
So while that's going around, the direction of the gravitational force is along the direction of the gravitational field, right? So on Earth, the gravitational field is pointing downwards toward the center of the Earth. Any object I drop, as we drop the Pepsi can, it falls straight downward. Similarly with the electric force, it's along the direction of the electric field. So the electric field is pointing down. If you have a positive charge, the force is going to be downward.
Does gravity ever repel two positive charges?
No. Gravity never repels. That's the unique thing. There are no positive and negative charges. There's only one kind, and it always attracts. So here you have two kinds. And as we mentioned last semester, you can also have three kinds. Like the strong forces that you have within the nucleus holding a proton together, you have red, green, and blue. You have the three types of charges there. Okay. So what's the direction of the magnetic force? So the red pencil, and when you do these things with the right hand thumb rule, have a couple of different colored pens or pencils. So let's say the B is pointing this way. And here is QV. So you have a charged bird. You picked up a charge and off it's going. Peregrine falcon, moving horizontally. You have an upward magnetic field. What is the direction of the force on there? Let's see if you remember your cross product and the right hand thumb rule. Strong force, isn't it?
What's in this again?
It's filled with lead.
Oh.
It's filled with lead. That's why. So instead of so, which is lead is heavy. You have 13 times heavier than water, and then that's absolutely goes.
Do you know how much it weighs?
No. What is this? 5 pounds? You can probably calculate it. Okay, so a thinker question for you guys. You go ahead and write this down. Here's B, so B is this thing over here. My charge is the blue pencil here. So you have an upward magnetic field. There's a bird that's flying, which is charged, is going to the right. So show me what the direction. So draw this. Draw on your finger sheet the direction of the force. So the bird flying this way, which way will the bird get pushed? Yeah, so there's an upward magnetic field. How is it upward? I mean, I can hold the magnet. This is the North Pole. I'm holding it this way. So it's shooting out an upward magnetic field. There it is. So there's my little magnet, the small one over here. Then there's a bird that's flying this way. It's positively charged. It's flying horizontally. So show on your diagram the direction of the force on that bird. The charged bird. Going back to the cross product, think of torque, right hand thumb rule. Okay, so Jackson, you want to take a guess?
So for the right hand thumb rule, you point your hand away from you, right? Like this. And then
Okay.
I'm also I'm definitely not positive on this. And do you point your fingers in the direction of the charge?
So the easiest way, this applies to any two vectors, not necessarily just a magnetic field and a moving charge. If you just have any two vectors, A and B, A and C, let's say. The cross product, first of all, is perpendicular to both of these. So if you put it in a plane, the result is either this way or this way. So it's a line that's perpendicular to the plane of these two vectors. Now the question is it towards you or away from you? That's where the right hand thumb rule comes in. So you curl your fingers from the first to the second, if it's C cross A. If you curl it this way, then my thumb is pointing toward you, and this is the result. So the final vector is pointing towards you. So notice it's pointing in a different direction. But isn't it strange? You have a magnetic field that's going upward. You have a charge that's moving this way. The magnetic field is not pushing the charge up. It's going to push it towards you or away from you at a direction that's at 90 degrees. So let's see a video of a demonstration of that. So here, if I make this bigger, this is a cathode ray tube. the CRT. Have you heard of CRT TVs? Before the flat panel TVs, they had this big thing which is like a huge, heavy glass bubble. We have one such TV at home. It weighs like 200 or 300 pounds, the 55-inch TV. But you needed something that was evacuated. So you pump this down. So the glass had to be fairly thick. That's why it's so heavy, actually, the weight of the glass. You pump this down, and then you have a cathode here. So a cathode is what loses electrons, if you're going back to the battery over there. So normally electrons will not jump off a metal. They're bound there. But if you heat up that metal, the electrons will get boiled out, basically. And those are accelerated. You have the beam of electron, and it goes and hits the screen over here. And in the case of a TV, you had magnetic forces and electric forces over here that could move the beam around. So it would basically scan the whole screen. And that's how you form your picture. So this is before having individual pixels and flat panel display. But here, instead of having a perfect vacuum, you have a little bit of gas in there. Low pressure, almost vacuum that you have there. So as the electrons go through this, they produce a glow. So you can see the path. You can see the path change. So watch this thing as they bring a magnet close to it.
Watch what happens when I bring a magnet near the beam. The beam deflects, which shows that there is a transverse force due to the magnet on the moving electron. In general, any charged particle that is moving in a magnetic field will experience this fundamental.
Do you see how odd that is? You have a magnetic field coming like this. Shouldn't the beam be pushed away, attracted? It gets pushed at an angle that's a 90 degrees to both the beam and the direction of the magnetic field. That's where the cross product is coming. So it actually happens. It's very odd, but that's what's happening.
Fundamental magnetic force. The beam deflects, which shows.
So this is the nature of the magnetic force. If you have a moving charge and you have a magnetic field, instead of magnetic field pushing the charge this way, it experiences a force that's at 90 degrees to both V and to B. Any ideas as to why this could be? What would cause such a strange force, combination from these two things? Nobody knows. Sorry, I was saying something before.
Maybe just like the magnetic field curves really hard.
No, but so this happens even with a straight magnetic field. Like with a capacitor, how you had a parallel electric field, you can have a very parallel magnetic field, uniform magnetic field. Like in the case of the Earth, it sort of points northward. It's pretty uniform throughout the side of a town, for example. Go ahead.
Is it because where the magnetic field is coming from is so strong, pushing it?
So in the case of a uniform magnetic field, you have an additional effect. But this happens even for a uniform magnetic field. If it's non-uniform, that's an additional effect actually. But this occurs even for an absolutely uniform magnetic field. It's at 90 degrees. And why does it do it? It just does it. It's a physics law. It's a fundamental physics law. It's the way nature behaves. And this is the magnetic force law. So that's just the way it works. Oftentimes you have a combination of electric and magnetic field, then you have combined forces, something called the Lorentz force, but we won't get into that. But that's the magnetic force law, and that's just the way the magnetic fields operate. So remember that physics laws, fundamental laws, they don't have to be intuitive, they don't have to make sense. Nature can do whatever it wants. And usually you have an intuition built up from common experiences. Now, how often do you experience a situation like that, like electron going through a vacuum and things of that nature? That's why it seems odd and counterintuitive. But laws don't have to be intuitive. They are what they are. Now, if you sailed, by the way, this would not seem so surprising. In the case of sailing, like if this is the beach, and then here's the ocean, and there's your sailboat. It was meant to look better than that, but anyway. So the breeze, the sea breeze, is usually in this direction. It's perpendicular to shore. That's why sailing offshore for a long, straight coast is kind of the easiest ways of sailing, because you have a consistent wind always in one direction, and a consistent magnitude as well. But the boat is going in this direction. So boats routinely go perpendicular to the direction of the wind. If the wind is behind you, it's a different kind of a sail. It's called a spinnaker. It's like a big rectangle. It's just getting pushed. But with different kinds of sail, you can go perpendicular to the breeze over here. So since most people don't sail, it seems kind of odd. But that's the nature of the magnetic force. It's perpendicular to both. Okay, any questions?